Okay, so before we begin the explanation for S25, there is key assumptions that we have to consider and why I'm considering these assumptions. So one thing which I like to clarify is something called as the attacker versus receiver space. So what usually happens in a quantum communication system is that the receiver receives one message while the attacker receives a combination of very close messages. So for example, if I have the receiver receiving a message such as 122112, the attacker can receive message which is very close to this. For example, 122110. Again, these are very specific numbers which I'm going to be going into much later on. But these numbers, so the attacker does not receive a perfect copy of the receiver space. So then what he would be seeing is 122110 as well. Sorry, 12, which is the intended message. But also he sees 102112 and then 302112 and so on. There are many such combinations, but I mean it's not going to be 30, it's going to be 32. So again, there's a very specific reason why I'm choosing only one of the digits to be different, which I'm going to be explaining. But before we go into that, we need to look at some setups. So let us look at the cross section of an optic fiber. Just draw it a little bigger. So again, so the optic fiber, what happens is the rays go in at an angle which is going into the board and also at one of the mirrors. So this is of course a reflective surface. So once it hits one of these mirrors, it just keeps on oscillating. So it may go like this, and so on. So what that creates is, if there is a bit, then I'm going to send the actual pulse through this, and it just keeps on going in a helical shape, and it just keeps propagating. So that is the setup of the optical fiber. So now let us look at a reasonable qubit transporting system or the qubit creation system. So what most likely would happen is, we are going to be having a laser, and then I'm going to introduce a polarizer. So of course this is going to be a Gaussian beam, and I'm going to introduce a polarizer. Then I'm going to be introducing the crystal. So this is something called as an electro-optic crystal, which actually rotates the polarization once you apply a particular amount of electricity across it. So let me just put this as plus and minus. So yes, so the laser light is going to be a coherent source. And then the polarizer gets rid of all the slightly varying polarizations, and then it passes through an electro-optical system which actually rotates it, and let's say there's some propagation unit. So what exactly is this propagation unit? There's another speculation. Propagation, and then what I'm going to do is I'm going to be putting in a polarizer. So now, how do I actually, I mean, what this polarizer does is it measures it. So this laser is going to be, the beam is going to be acting as a qubit. So if I take the particular polarization, I can just say that the in one of the directions it is going to be 0 and the other direction is going to be 1. So I'm going to polarize it such that the qubit is going to be in one direction. Let's say it is going to be in this direction. So the electro-optical crystal rotates it around the other direction. Let me just. So after the electro-optic crystal, let's say I get one of these two. Of course, this, if you can remember, this is from the Heidelberg gate, and this is from the X gate. So this is going to be 0, and this is going to be 1 plus 0 over square root of 2. I just forgot the question, and this is just going to be 1. So this is how I'm going to send my qubits. And of course the propagator is there, then I'm either going to trap it in a quantum dot, or I'm going to, if I want to immediately measure it, I'm just going to put it through another polarizer. And of course, I'm going to make it so that I'm going to be detecting either 0 or 1. So of course this can be done using because of the properties of this described by Young's double slit experiment. Okay, so this is how the actual qubit is going to be prepared and sent in a, let's say it's a realistic system which is going to be developed very soon. Yeah. So why do we require a laser? So if we just take a normal light source, the polarization can be in all different directions in this. So let me just use a different color. So the polarization can be in any of these directions. And the thing is, if I want to propagate a particular qubit, the qubit is actually information stored in the direction of polarization or the angle of polarization. So what happens is, if I were to use an electro-optics, if I were to use a fiber optic setup, what happens is every time it bounces or every time it reflects, it undergoes a rotation. So let's say that let's just include a mirror, and light will just polarize in this direction. So as the light actually reflects off, the polarization switches. Because I can just, if we look at the propagation of the wave, this is just going to pass through without it, and then it's going to be reflected. So the actual polarizations are going to be in this way, which means that there is rotation applied, rotation of polarization whenever I hit a mirror. So which we do not want. So, and another thing, I don't want this kind of a polarization. I want it to be uniformly polarized in one direction. And of course, lasers are the only things known right now to produce a coherent beam, which also has a particular polarization. So that is the use of the laser, and the electro-optic system is to actually change the angle of polarization. And yeah, so this is the basic setup of a transporting qubit. Now let us look at what the propagator is actually made of. Of course, there are many such um, ideas or things to be present. But for cryptography and for communications, there is going to be a type of system which is going to be much more efficient and much more of what we actually want in a qubit, which is that the attacker cannot just access it. So, how this system works? Again, this is designed by me. Before that, we need to look at some models of self-focusing. So a property of laser is that when it passes through a non-linear optical medium, it can either focus or defocus, depending on what the actual N2 or the second order refractive index is. So eta is going to be equal to N0 plus N2i. I mean, this is the system which actually we are talking about either focusing or defocusing or filamentation, that kind of setup. So, yeah, so if this is the diffractive index, of course it's dependent on I. This also becomes very important later on when we are looking at beam splitter introduced, and because this is going to change, the intensity is going to change because the beam splitter is actually going to divide the intensity. There's going to be change in eta at the very end, which also actually plays a very important role. And so what happens is Uh, so of course we have something called as power, critical power and power of the actual beam. So let's say I have, so according to the theory, once we actually solve for this, what we are going to get is if the input power is much greater than the critical power, we are going to be seeing some sort of a filamentation, or everything just focuses on one point and the material is going to be under a lot of stress. But if we are going to have critical power to be somewhat around the input power, we are going to be looking at a system which just barely focuses it. So again, if I keep putting these in series, then I can actually focus it, and the final beam is going to be this way. And then it just keeps on going through the same thing. And of course, the polarization is preserved, and all of the characteristics are somewhat fine for this. Um, so, what exactly, I mean, like, where we use this currently right now is something called as curl length mode locking. So, we do have systems which have multi-kilometer focusing models of curl lengths. Of course, this is done in air. And yeah, I mean, we can look at the equation for critical power. And what we see is that this is somewhat equal to uh, Pi over ECR is somewhat equal to around 1.5 to 2 times of the, I mean, yeah, the ratio is 1.5 to 2. So what this does is this creates an unstable kind of focusing, where that let's say that there are some other losses which I have not discussed right now, particularly beam splitter. So if I just put in a beam splitter here and it's very sensitive, the beam actually completely diverges, and the the receiver knows that the beam has been tampered with. So that is one way to go. And yeah, so but there are some instances where I can just take a very very small sample, and then I can find out what exactly these qubits are. So I came up with this kind of a system. Of course, it's the same media that we're using, and if this is the propagator, there's going to be one laser which is going to be pointing in this direction, and the other laser which is going to be in the opposite direction. So what this does is, again, this is somewhat like borrowed from the optical fiber setup. So what this does is it forms a shell of a laser. Of course, these are CW lasers, and this kind of forms a shell. So once we look at the cross section of this propagator, what we see is that this is actually completely filled with two overlapping lasers. So there are lasers which are going in one direction and the other direction as well. And also there are, because this CW is also going to be Gaussian, there's going to be all sorts of K polarizations which are going to go in this shell. So now what that does is, once I put a, and this part is where the actual beam is going to be propagating. So now imagine a beam splitter here. Of course, then it just splits the beam. Uh, so what exactly happens when it comes through the powerful shell? So it undergoes degenerate four-wave mixing, or n number of, I mean, in this case it's a four-wave mixing, but in a normal case where there are multiple K polarizations, let's say that I have summation of Ki number of polarizations, and then all of these are going to be creating some sort of an interference which will polarize this particular medium, and K polarization is going to be equal to K signal. So this is the K signal, and of course because of all of this, there's going to be some K polarization, arbitrary K polarization. So I don't angle. Let's just put an arrow here. So we have some arbitrary angle of polarization, and then we are going to be, sorry, this is the, it actually follows the excite probe geometry. So this is K probe. So let's just go through what the excite probe geometry is. So we have two strong lasers. So this is KEX1, KEX2. So this actually forms a grating of some sort. And then this is the K probe. This is the K signal. So when we apply this sort of thing to this model, we see that whatever light is being reflected by the beam splitter or being stolen by the attacker undergoes this. And because K polarization is unpredictable, the K signal is also being unpredictable. So this is the best chance of deterring an attacker because he doesn't know. So now, what is so great about S25 is that we are going to minimize this error which is being done to the attacker. We are giving the attacker as much information as possible with this constraint in mind. So now the actual assumption, which I'm going to call as MMI minus 1. So this assumption states that if there is an attacker and there is a receiver, so if I have some n number of qubits being received by the attacker, sorry, received by the receiver, then the attacker at most can gain n minus 1. Or there is one bit of difference here. So this causes an asymmetry in the attacker and the receiver space, which I discussed in the very first part of the module. Yeah, so this actually solves one of the greatest problems in quantum cryptography, which is called as number splitting attack. So what the attacker does is he just puts a beam splitter and then he uses an X gate. So they say that these are the qubits. So there's going to be reflected and transmitted. Of course, the reflected are going to be switched over, and then you can use either an X gate or a Z gate depending on the geometry of the construction. So yes, so this does help in number splitting, and this takes it to the maximum, which means the receiver doesn't actually know about this attacker presence, but the attacker somehow manages to get n minus 1, which is really not the case because the receiver can look at the bit error at the very end of the propagator. So what happens is there is going to be some sort of acceptable noise limit for a qubit. Of course, that noise is determined by the distance and the actual quality of the quantum channel, etc., etc. But we do have some sort of measurements that we can make to make sure that this the receiver has some idea about the errors or noise in the channel. So usually what happens is in these kind of noisy systems, if I send m qubits, I'm going to be receiving n number of actually useful qubits once I apply the error correction. So this error correction is going to look at the noise and everything, and m is of course greater than n, of course. And then let's say that there are some parity qubits which can be added. That is fine, but this is the actual assumption, and the reason behind this is given before. And yeah, so now let us just look at the existing quantum cryptography algorithms and what MMI minus 1 does to it. So I'm going to be discussing only about BB84. Of course, I can look at what happens in SARG 06 or 04, maybe even low Chow protocol, and all of them are kind of similar in the sense of how they actually work. So in Let's just do a rundown on BB84. So one is, let's say that there are A and B. So A prepares A prepares these kind of states in different bases. So we'll just call it beta XX. Of course, this is not the exact thing, this is just being a little bit modified, but this is usually beta 01. So what, sorry, beta 00. So let me just write down what is beta 00 over here. So we prepare this beta 00 in different bases. So I'm just going to put a bracket here and say this is 01 basis. So A prepares beta 00 in two bases. So now, what does beta 00 in another basis look like? So I'm just going to take plus and minus. So what's interesting about plus and minus is, if I were to create a qubit in this basis, I'm just going to get 00. That is the actual definition. Okay. So A prepares beta 00 in two bases, and then of course he does not. These two bases are going to be randomized. So let's say that A throws a coin, and if it lands on 0, uh, then 0 1 basis, and if same thing is equal to 1, then plus or minus basis. So after preparing this, A sends B the second qubit. So this is qubit number 1. So A sends B the second qubit, and then based on okay, fine. So let's just start from there. So A sends B the qubits, and B applies the error correction codes, and both do. ECC stands for error correction circuit. Then the third step is what A, of course, measures. He knows exactly what the bases are. So what he does is he measures in the exact basis that he sent. For example, if he sends 0, then he is going to measure the qubit in the basis 0 1. And if he sends it in plus or minus, he measures the qubit in plus or minus. So A measures it in whatever state he has sent, and B measures it in some another random sequence. So B also applies the same thing, and then so now what A and B do is they come together and then they check what are the exact values that they have gotten, and then they choose. Uh, So the code is chosen based on what if this and this actually match. So if the qubit measured is beta 00 in 01 state by A, and then B also measures it in 01 basis, then we say that it's a part of the code. Otherwise, it is not. So let's say beta B measures it in plus or minus state, whereas A measures it in 01 state. Then we say that it is not the actual code. So now let's just look at post measurement state for both of them. Um, of course, this is very important because it can be a little confusing in the plus or minus case. So here, if A measures 0, and then B measures, sorry, if A measures 0, then B also measures 0. That is obviously a given. And then if in this case A measures plus, then B also should be measuring plus. I mean, after all of the uh, gates exchange and whatever it is. So that is in the teleportation circuit. So after the teleportation, if they get the correct, I mean, if they measure that one particular value, they get the exact same thing. So again, if B measures plus and A also should be measuring plus here. So if there's a mismatch, so let's say A measures plus and B measures minus, then of course we know that it is not part of the code, and then we just ignore that. Okay, so this is the overview of BB84, and let us look at what happens under MMI minus 1. So yes, so we looked at the BB84 protocol, and now let us see what exactly happens when I apply this particular thing in both attacker and receiver space. So I'm going to be using zeros and ones, and then we can follow along what exactly happens. So of course, so in S25, what I've done is I've looked at only one of these, and the attacker knows exactly which is the uh, qubit that is wrong. I mean, there's an ambiguity of one bit, but in actual case, the bit might be anywhere here, or it might not even exist at all. Of course, that is very which I'll be coming into later on. But in this case, so let's say that the receiver sends some message in English. So let's say, um, so this is some arbitrary code, and this is how the attacker looks at all of the combinations. So let's say the message after sending the code is meet me at 5. And now we are going to look at what the attacker actually says. So when he does it, when he does the exact same thing, what he sees is me. So now we arrive at the problem behind BB84 and MMI condition. The attacker sees all of these things. Of course, the actual key is different, but once we actually encode it and the attacker kind of decodes it, we are going to be left with this kind of a situation. So now, if I look at this situation, there's only one possible value that this entire thing can take, which is the exact value. Of course, there's very little chance that the actual, I mean, these words are not as important as this one. So let's say that an attacker wants to know exactly the time, and of course, when the attacker looks at this kind of a state, he's going to say that okay, 5 appears in most of the time. So what I'm going to do is I'm just going to leave out all of the 6 and then just keep 5 in it. And of course, this is a problem, and it kind of looks impossible to solve. Um, but we can try our best using S25. Okay, so that is the explanation of what MMI minus 1 is. and of course it doesn't work in classical because of the optic fiber setup. Uh, and yes, this is the kind of thing. Now let's just have a look at the four or three categories of post quantum cryptography, mainly to solve this kind of an issue. So these are methods where we introduce P versus NP problems in order to actually hide the answer. So one is lattice-based cryptography. Second one is hash-based. Third one is collision-based, and the fourth one is code-based. So these are all the existing algorithms that we can implement in order to mitigate this effort. So one is lattice-based cryptography, where you use an arbitrary lattice and look at distance. So what we do is we take a particular material or metal or semiconductor or whatever, and we introduce some abnormalities in the lattice. And then after introducing the abnormalities, we look at the closest distance between 2 points, whether it is Euclidean distance or Manhattan distance based on what the actual lattice is. We can use that, and because this is still an unsolved problem in mathematics, this can be used as uh, a good quantum cryptography, because quantum systems still have a problem in that particular field. So the second one is hash-based cryptography, where I take a code and then I put it through a hashing machine. So hashing machine takes the code, and based on the code, it transforms into other uh, some other what is it, bits. So if I have a particular code, based on what the actual code is, it provides a one-to-one transformation to uh, another code of some length. So of course, this is based on a particular map. So every code is going to be mapped into one of the other codes, and then if the map is shared between the attacker and receiver, then it is very hard to actually um, get back the actual code. Okay, so the next one is collision-based cryptography. This is similar to how S25 works, but it's also not. So what this relies on is collision between passwords. For example, let's say that there's a four-letter word which I'm trying to send it to the receiver, and it starts with L and dash dash K. I mean, this can be anything. So this can be look or lock or some other uh, possible combination. So these are called as collisions. And finally, code-based cryptography looks at different kind of ECCs. So the error correction codes are going to be the ones which are actually securing the final code. Yes, of course, they all have some internal problems, and especially this hash-based cryptography, because with a very powerful quantum computer, I can look at all of these transformations, and then I can select the one that actually works. Um, yes, of course, it's going to take some time to break it, and yes. So for collision-based cryptography, they require a very high amount of um, ambiguity in the actual final message, which we are not looking at. We're looking at just one bit of ambiguity. Of course, code based is you have to somehow transport all of this code, and the error correction codes may fail, they may not fail. But yes, this is a very powerful system. But there is a way to amplify this even more. So that is the assumptions and the physics behind what we're looking at in S25.